In this module, you will learn about the applications of the common ion effect. You have learned that in a saturated solution, if the concentration of any one of the ions is decreased, then, as per the Le Chatelier's principle, more salt dissolves and the equilibrium shifts towards the right till Ksp becomes equal to Qsp. On the other hand, if the concentration of any one of the ions is increased by adding an electrolyte, then the equilibrium shifts towards the left according to the Le Chatelier's principle till Ksp becomes equal to Qsp. The common ion effect is used for the complete precipitation of one of the ions as its sparingly soluble salt with a very low value of solubility product for gravimetric estimation. For example, silver ions are precipitated as silver chloride, barium ions as barium sulfate, and ferric ion as ferric chloride or ferric sulfate. The common ion effect is not only used in the quantitative analysis of compounds, but is also for their purification. For example, sodium chloride, along with impurities such as sodium sulfate and magnesium sulfate, is purified by applying this principle. When hydrogen chloride gas is passed through a saturated solution of sodium chloride, the precipitation of sodium chloride increases and dissociation of sodium chloride decreases due to the chloride ion, which acts as a common ion. Thus, the sodium chloride obtained is free from impurities. The solubility of salts of weak acids, like phosphates, increases with an increase in the concentration of H+ ions or a decrease in the pH. This happens because the anionic part of the salt reacts with H+ ions to form the salt, such that the equilibrium shifts towards the right side. This means that the solubility of the salt increases so as to make Ksp equal to Qsp. Now, let's derive a relation between the solubility and H+ ion concentration for a mixture of a weak acid and its salt. Let's take a mixture of weak acid HX and its salt MX. MX ionizes to give M+ ions and X- ions. Then, Ksp is equal to the product of molar concentration of M+ ions and X- ions. HX ionizes to give H+ ions and X- ions. Then, Ka is equal to product of molar concentrations of H+ and X- divided by HX concentration. On rearranging the equation, we get X- divided by HX equal to Ka divided by H+. Taking inverse of both the sides and adding 1, we get HX divided by X- plus 1 is equal to H+ divided by Ka plus 1. This can be written as Hx plus X minus divided by X minus is equal to H plus Ka divided by Ka. Now, on taking inverse, we get X minus divided by X minus plus Hx is equal to Ka divided by Ka plus H plus is equal to F. At a given pH, if the solubility is taken as S, then Ksp is equal to the product of S and Fs. That is, equal to product of S square and F. Therefore, solubility is equal to square root of Ksp divided by F. On rearranging the equation, we get solubility S is equal to product of Ksp and H plus Ka divided by Ka whole to the power half. So we can conclude that solubility increases with a decrease in pH or an increase in H plus ion concentration. You have now reached the end of this module. In this module, you learned that the solubility of an electrolyte in water decreases on addition of an electrolyte that has one ion in common with the electrolyte. This is known as the common ion effect. The common ion effect is also used for the complete precipitation of one of the ions present in a solution as its sparingly soluble salt. The solubility of salts of weak acids increases with an increase in the concentration of H plus ions or a decrease in the pH. The common ion effect is one of the applications of the Le Chatelier's principle.